To get the idea here, we're going to look at an example where a region that is 40 degrees north of the equator averages a minimum of 8 hours daylight in December. Hours of daylight are at a maximum at 16 in June, and we're going to let X represent the months of the year with 1 for January, 2 for February, 3 for March, and so on down to 12 for December, where if Y represents the number of daylight hours in month X, we're going to use a sine function of the form y equals sine bx minus c plus d to model the amount of sunlight. So we're not going to talk about it in great detail in this class, but there are a lot of important things that can be modeled cyclically in terms of sine and cosine. Because there are a lot of things that follow nice, semi-nice, semi-repeated patterns that can be back-ended into describing with these kind of wave functions. These have nice behaviors that are very good to work with for some advanced and complicated things. For now, because we're still just getting started, we're going to see how we can handle this type of situation, where our goal, because we want to set up a model in that form, is to be able to find the values for A through D. Well, what we need to do here is think about what we have. Because we are told that the maximum value is 16 hours and the min is going to be 8 here, we have that our function is going to oscillate between a top of 16 and a bottom of 8, which means that our middle, because we're using a sine curve, is going to be the middle of 16 and 8, or 12. So our amplitude A is equal to 16 minus 12, or 12 minus 8, whichever you prefer. In either case, we get that the value A is going to be equal to 4, while because we're pushing up to that value of 12, because our middle is right there, we also get that the vertical shift D is 12. So you have to have been pushed up that 12 somehow, and the only way to do that is in terms of a vertical shift. To get B, since the period, that is a year, is 12 months, all we have to do is recognize that our period 12 is equal to 2 pi over b, multiply b over, divide by 12, and what we'll end up with is that b is equal to 2 pi over 12, or pi over 6. Now, at this point, we have A, B, and D. And all we're left with is to be able to find the phase shift C. And that's probably the hardest part here. It's the one that takes the most subtlety. Where to do this, we have to understand the behavior of a sine function. We have to understand that because sine starts, that is, you can think of the period, the initial period, as starting in the middle. That is, it's in that midsection between a top and a bottom. And March is the month between our minimum and our maximum, between December and June. We must have that our phase shift is equal to 3. Because we said that 3 is the x value for March. And as a result, we have that 3 is equal to c over b, or c over pi sixths, which is the same as saying that c, in this case, is pi over 2. So if we want our complete picture, we will get that our function has form y equals 4 times sine of pi over 6x minus pi over 2 plus 12. And that's all we have for this section. As I said a bit earlier, we're not going to be doing much specifically in terms of 4.6. I would still strongly recommend looking at 4.6, especially into the tangent function graph, as our last section for this chapter that we're going to really spend much time with is 4.7, where we're going to be looking at how we can take the inverse of our trigonometric functions. We'll see that next.